Alright, so we start with the question, which of these molecules is polar? And what you're going to do first every time is add up the number of electrons. So SO3 has 24, and then you're going to want to go ahead and draw the Lewis structure. So the least electronegative atom is going to go in the middle, and then the more electronegative atoms will go on the outside, and then you're going to fill these shells with electrons. And what you're going to find out is that these actually are going to make a third bond right here. And like one of these pairs is going to go away and it's going to like rotate around. And what's important about this is that it has trigonal planar geometry. So when you draw these dipoles, it's going to be one going here, one going here, and one going right there. But they're all going to cancel each other because these angles between the two molecules are going to be the same. So there's no net dipole, meaning that the molecule is nonpolar. And for OF, we're going to do the same thing. That's actually OF2. We're going to count the electrons, so it's going to be 20. And then the least electronegative followed by the more electronegative. And this one is actually going to have two non-bonding domains on the F. And these non-bonding domains are going to push these two bonds away. So it's going to end up looking like this. And the net dipoles are going to be this way. So that's going to make a partial negative charge on these fluorines, and the oxygen's gonna be positive. So you can do that little delta thing. And when you see that there are net dipoles, that's always gonna mean it's a polar molecule. Now, a common misconception would be not to draw this structure right, and just draw it like this and think that the net dipoles would cancel. But in reality, these non-bonding domains are going to push the atoms farther away, and that's going to create the polar molecule. So that's something to watch. Now, the next one is BCl2. So once again, it's going to have 16 electrons, and we're going to start with the least electronegative. And then we're going to add our electrons in. And what we're going to see here is that since these chlorine atoms are more electronegative, they're going to have a slightly negative charge. And this Be is going to be slightly positive. But since there are no non-bonding domains, unlike the oxygen, another common misconception here, these net dipoles are going to cancel. Because this is bent. Oh, not bent, my bad. Linear. So both these bond angles are 180 degrees, and the dipoles cancel. So this is going to be a non-polar molecule. So once again, watch that common misconception to draw these Lewis structures wrong. You need to watch the non-bonding domains and how they affect the atoms. Because as we can see, if there aren't non-bonding domains, it leads to a non-polar molecule. So our next compound here is CCl4, which has 32 electrons. And if we draw this with our least electronegative in the middle again, and then go ahead and add our electrons. We're going to see that all of these angles are the same, and it's going to form a tetrahedral because it's got 4 domains. But what's important about this tetrahedral is all of these chlorine atoms have the same electronegativity, so they're going to have the same dipole movement. So the up will go with the down, and you have to remember another common misconception, these are three-dimensional molecules, so it's not going to be like this. There's going to be one coming up, and then like one this way, one that way, one going back, and then your carbon's right there. But when you draw your Lewis structure, it looks like this. So remember that these are three-dimensional molecules. Common misconception. And when you look at these net dipoles, you're going to realize that they all cancel, which, as we discussed before, leads to a nonpolar molecule. And the last thing we have here is O3, which has 18 electrons. And like this first molecule that we talked about, you're going to have like a half bond right here, which we draw by the dotted line. Make sure to watch those. Oh, my bad. There you go. And what you're going to see is that that's going to lead these to have a like slightly negative, and this is slightly positive. But since this is bent geometry, there's no net dipole movement because these angles are going to be the same in between these molecules, and they're going to pull the electrons the same amount. So when you have no net pole movement, dipole movement, you're once again going to have, oh shit. Alright, just kidding. Actually, you're going to have a non-bonding domain up here, and that's going to push these away. I thought that looked wrong. And this O is going to kind of move. And since these are not at a 180-degree angle, there actually is dipole movement. And that's going to lead to a polar molecule, which, like, it's kind of confusing how the domains work out, but you just need to know that since it moves these bond angles from 180 degrees and the bent structure, not linear. See, this is linear, nonpolar. This is bent because it has three domains. So it's going to end up being a polar molecule. My bad about that mistake. I was looking at the wrong notes. So once again, to go over some common misconceptions, make sure that you draw the correct Lewis structure and you add your non-bonding domains and how those affect your electrons. Always check your domain geometry and molecular geometry, and it's helpful most of the time to draw out these dipoles, because when the dipoles cancel, you're going to get a nonpolar molecule. Important to note. So that's how you determine which of these molecules is polar.